2.3 is chemical formulas. We are going to spend the remainder of Chapter 2 reviewing every single piece of naming information that we covered last year. So this is going to go about naming general compounds like NaCl is sodium chloride, CO2 is carbon dioxide, PO5 would be phosphorus pentoxide, HCl would be hydrochloric acid, HNO3 would be nitric acid. We're going to refer, and then in the we'll break this into two sections. In the second of the two sessions, we'll review how to name those organic molecules that we did at the very end of the year last year. So, a little refresher on chemical formulas. Remember, the subscript is always to the right and it tells us how many we have. So if we have a number like H2O, the 2 is telling us that we have 2 hydrogens. All right. Molecular compounds are composed of molecules and almost always contain nonmetals. Just a little reminder there. So H2O is a great example. 2 nonmetals, hydrogen and oxygen, carbon monoxide, carbon dioxide, and it continues. Now, one thing to remember that when we are talking about elements, there are 7 elements on the periodic table which bond with themselves and exist naturally as diatomic molecules. And the 7 are listed there. One of the ways you can kind of remember that is heck no halogens. And what I mean by heck no halogens is the heck is hydrogen, the N and the O are nitrogen and oxygen, and then the remainder are the halogens. So heck no oxygen, or heck no halogens is kind of a way to remember that those 7 molecules are diatomic, and anytime you write them, hydrogen is, H2, hydrogen would be F2, iodine would be I2, and that's how they exist naturally. So just a little reminder on that front. Empirical formulas and empirical formulas and molecular formulas. What is the difference? Empirical formulas give the lowest whole number ratio of each atom. Molecular formulas give the exact number. So for example, sugar, a simple type of sugar, is C6H12O6. That would be the molecular formula, because the empirical formula would be CH2O, because that's the lowest whole number ratio of atoms in an element in the compound. So just a refresher on empirical versus molecular formulas. Structural formulas, those are the Lewis dot structures. So if I'm going to ask you to draw the Lewis dot structure of a compound, that'll be the structural formulas, and they can get a little more intense than what we had last year. Right here we have CH4. Here's the basic Lewis dot structure for CH4. However, if we're kind of going to do a perspective drawing, we're going to show how that's actually going to look. So there's a variety of perspective drawings that we can give to kind of imagine it. Now, they really prefer in these slides using these geometric configurations for a lot of atoms. So structural formula is just the Lewis dot structure. Perspective drawings is kind of a 3D arrangement of how they would look. When we talk about ions, remember we have 2 types of ions. We have cations, we have anions. Cations are positively charged, anions are negatively charged, and there's a wide variety. Instead of spending time going through this on Moodle, you can find the updated pink sheet, and you will need to know the pink sheet just like you had to know it last year, except that I've added to the pink sheet because this year it's required that you know a few more polyatomic ions. So just kind of keep that in mind. That's updated. We'll go through that. There will not be a formal quiz like there was last year. It's just that you have to know that. That information will not be given on the AP test. That needs to be common knowledge. When we talk about bonds and we talk about ions, here's a simple definition. One of the things they're going to ask you to do on the AP test is compare different types of bonds, and you need to be able to distinguish ionic bonds from covalent bonds. Well, how do you do that? An ionic bond, very generally put, is a bond between a metal and a nonmetal. So you know that salt, NaCl, table salt, NaCl is an ionic bond, but you know that just from common knowledge from last year. Na is a metal, Cl is a nonmetal. So that kind of works, but they may give you a compound like, let's see here, tin fluoride. How do I know if that's an ionic bond or covalent bond? Well, tin is a metal, fluorine's a nonmetal. It's definitely an ionic bond. So you have to be able to identify the difference between ionic and covalent, and this is one of the easiest ways to do that, is ionic compounds, metal and a nonmetal bonding together. Writing formulas, we shouldn't have to spend too much time reviewing writing formulas. Just make sure that you balance the charges. The charges have to, a compound has to have a charge of 0. So just real quick, if we had, well, we'll take the last example I did. We had tin plus 2 and iron minus 1. When I combined them together, I had SnF2. Just a general review. If you have questions on that, please ask me individually in class. I'm not going to spend a lot of time on that because I'm confident in your ability to do this. Here's a list of common cations and common anions. I'm not going to spend a whole lot of time on that because, like I said before, I posted on Moodle the updated pink sheet of all the charges that you're going to need to know. One thing I do want to point out, though, and a trick that I didn't show you last year, is kind of this. What we have, I kind of jumped the gun and I'll go back. I apologize here. What you'll see here is that when there are two oxyanions involved in the same element, the one with fewer oxygens ends in "ite," the one with more ends in "ate." And we talked about this last year. Sulfate, sulfite, nitrate, nitrite, phosphate, phosphite. But the one thing we didn't talk about was kind of where they exist. So a maximum of 3 oxygens are in period 2. So if you look at the elements that exist in period 2 on the periodic table, you have carbon and you have nitrogen. Well, when they're bonded with oxygen, you get carbonate and nitrate. The maximum number of oxygens that period 2 can hold is 3. So carbonate is CO3, nitrate's NO3. Nitrite would be NO2, carbonate would be CO2. Now, period 3 can hold up to 4 oxygens. So when you look at the elements in period 3, you have phosphorus, sulfur, and chlorine. So phosphate has PO4, sulfate has SO4, and perchlorate is the ClO4 ion. So just kind of something to kind of keep in mind there as you are maybe reviewing and studying the pink sheet. Now, if we go back just a smidge here, inorganic nomenclature. How do we name something very similar? How do we name something like, well, let's go LIBR. Remember, with LIBR, you are going to name the cation first, which in this case is lithium. And the second one, you're going to change the ending of the anion to "ide," so bromine becomes bromide. Now, if you have metals, and this is an important step here, right here, and one that often gets left behind, if you have a cation with more than one charge, so metals such as iron or copper or chromium, just to name a couple, you have to put the charge in Roman numerals, or lead or tin or a couple other examples. So if we use the example here, PbF4. We have lead. Lead has 2 possible charges. We're going to name the ion as is. We have lead. Now in parentheses, we're going to put the Roman numeral. Well, what is the Roman numeral? The 2 possible charges for lead is +2 and +4. Well, we know fluorine has a charge of -4. If there's only one Pb atom, that means lead is going to have a charge of 4. So we're going to put IV in Roman numerals. It's going to be lead 4. And again, fluorine will change to fluoride. So kind of general review there when we are dealing with inorganic nomenclature when we have a metal involved in the process. Here's just kind of updating kind of the idea of chlorates and chlorites and the examples of whatnot. Now, when we talk about naming acids, remember last year when we named acids, the base 8. All right, you're always going to look off of the base 8. So this would have been sulfate or phosphate, nitrate, anything like that. If it is the base 8, if it has the same amount of oxygens, so if we have the same amount of oxygens, we're just going to change the ending to ic. So the ending will just change to ic. Now we look at that 8, and if it has 1 less, all right, so this is our number of oxygens, I should say. If it has the same as our 8, we change it to ic. If it has 1 less, we're going to change the ending to us. If it has 2 less, we're going to add hypo to the beginning, the prefix, and the ending is going to be us. And lastly, if we have 1 more than our base 8, we are going to change the ending to per in the beginning, and then the ending to ic. So real quick, if we do 2 examples here. We have HNO4. HNO4 is our oxy acid. And it's an acid because it starts with an H and it has an oxygen. What is the base 8? The base 8 is nitrate. How many oxygens does nitrate have? Nitrate is NO3. So we look at this rules, and HNO4 has 1 more. So our nitrate is now going to become per-nitric. If we do another example, just to refresh your memory, let's go H2SO3. H2SO3. SO3, what is our base 8? Our base 8 would be sulfate. Sulfate is SO4. So now we are going to go with the rule, our acid has 1 less. So now our acid, instead of being sulfate, is going to be sulfurous. I add kind of the ER in there, sulfurous. So sulfurous acid. So just kind of a review when you are naming oxy acids. Remember, you only do this when you're naming oxy acids. That's acids that have an oxygen. What is going to happen if you name just a binary acid? Well, what's a binary acid? It's just an acid that has H and another anion, such as usually a halogen. So we have HCl, HBr, HI. Remember, if you just have a binary acid, all you're going to do is you're going to change the beginning to hydro, and the ending is going to change to ic. So in the first example, we have HCl. H changes to hydro. Cl is chlorine. We drop the ene, we add an ic, we get hydrochloric. HBr, again, we name the hydrogen, hydro. Bromine, we drop the ene again, bromine becomes bromic, and our acid is hydrobromic. Remember, you only name the hydrogens when you have a binary acid, such as HCl, HF, HBr, HI. Other than that, you're not going to name them. When we had an oxy acid in these examples, we didn't name the H. We left it be. The only time you're naming an H is when you do a binary acid. Last bit of naming today is going to be focused around what happens when we have two nonmetals. Two nonmetals. Remember, and this exists all the time, so let's use the example of PBr5. PBr5. We have two nonmetals here. Now this is where the prefixes come into play. I've given you the table here to help you review the prefixes. You have mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, 1 through 10. How are you going to do this? Well, first things first is you just keep the name of the first element. So in our example here, we have PBr5. Our first element is phosphorus. And our second element is bromine, and we have 5 bromine. So what is the prefix for 5? It's penta. We are going to change the ending to bromine just like we did previously, and it's going to be to bromide. So this is going to be pentabromide. Now, occasionally, you will have to put a prefix on the first element. So if we had an example like, let's go P2O8. P2O8. Again, we have two nonmetals. We have two nonmetals, so this is the only time we use these prefixes is binary compounds with two nonmetals. P2O8. What is the prefix for 2? It's di, so we're going to go diphosphorus. And the prefix for 8 is octa, and oxygen will turn to oxide, so we go octoxide. Remember, we try and avoid double vowels as well. We're not gonna nitpick with the spelling of these, but remember that is kind of an important aspect. So that is about 3/4 of what we did for naming. 3/4 of what we did for naming. It's all review from last year. Tomorrow, where we'll pick it up is we will review these organic structures, but right now, that is the biggest part of what we did today, is almost review every piece of naming information from last year.